Okay, let's go to the second part of the 17th Vienna Deep Learning Meetup. Thanks for coming back from the break. Hope we also have our YouTube viewers back again. Our second speaker today is Christoph Götz, CTO at ImageBiopsyLab. And his talk is about enhancing the medical expert. Let's see what he's going to show us about deep learning in this field. Christoph, welcome.
Thank you. Thanks everybody for showing up after the break. And I'm going to talk about medical AI solutions for bone disease expertise. So just to give you a brief overview, so what we want to do is become the global leader in image analysis for algorithms that help orthopedics. And what we as a strategy have is focus on the deployment of useful AIs for doctors and research. And our goal is to basically bring the first algorithm which will be FDA approved to the market next year. And you remember maybe like another success story from Austria was My Sugar, who also made an FDA app, and we try to do the same with an AI algorithm. And this is kind of about the path on how to actually go there. Oh yeah, FDA means Food and Drug Administration. It's certification, like the CE sign on some medical, probably on these things as well. It just means that it works as expected and it doesn't kill anyone. So, and you can earn money with it in a clinic. Thanks. Yeah, so the motivation behind that is that this guy, President Dr. Rick Bryan of the Radiology Association, said that I predict that within 10 years, no medical imaging study will be reviewed by a radiologist until it has been pre-analyzed by a machine. So radiologists are pretty scared that machines will take their job, but to counter with a different quote, from NASA this time, man is the lowest cost 150-pound non-linear all-purpose computer system which can be mass-produced by unskilled labor. And that holds true for that as well. So basically what we're trying to do is like pull in all those safety belts where we right now say, okay, we drove without safety belts, no one would do that anymore. We will say in 10 years, some dude just looked at an X-ray and gave a diagnosis. That's kind of 2018. And so where is the state of the art right now? AI for medical diagnosis is just right now maturing. Like Wednesday last week, there was the first AI algorithm FDA approved, meaning you can sell it in a clinical hospital. And it kind of replaces the diagnosis by a physician. So in this case, it's like diagnosing diabetic retinopathy in scans from the eye. And so what we want to be in the future is a medical product like these things. But now, in our case, we would be an FDA-approved TensorFlow model. So how do we get in that league of products? And we're not the only ones trying to do that. Basically, the recipe is pretty simple. These guys applied the following algorithm. So you choose a combination of three things. You choose a modality like MRT, CT, X-ray, or ultrasound, which gives you images. Then you pick a body region, and then you do either diagnostics, some measurements, anomaly detection, or improve the workflow in that field. And what we do is basically we focus on bone diseases on X-rays. And bone diseases themselves are pretty debilitating. They're like a whole bunch of them, and an aging and fatter population demands like proper solution for that, because what happens is you get, for example, osteoarthritis. It affects actually 15% of the population, and what happens is that the cartilage in your joints just degenerates and causes tremendous amount of pain, and at some point you gotta chop off your knee and get a replacement. It is the greatest cause of disability in the US, and it's a huge burden to society. And you can't stop it, but for that, the cartilage still has to be there, so you have to diagnose it in an early stage. But if you look at radiographs, it's pretty hard for humans to pinpoint the early stages of the disease. And what happens is usually people are much better at diagnosing this case, and you can rather like see yourself that there's, well, this knee is done, bone on bone. So still, people are trying to do that every day. 40 million knee X-rays in Europe alone every year. But more information does not necessarily mean better decisions. So quite on the contrary, more images mean more errors. And if they work under pressure, they increase their error rate. So that's where we come in. We do automated image analysis that saves time and enables better decisions at the same time. And that's our product. We are already at the market. We sold to radiologists. So what you get out at the push of a button is a standardized real-time knee osteoarthritis imaging biomarker. Biomarker, you can think of it as like getting your blood drawn. Back then, some guy had a look at the slide, counted every cell. Now that's automated. No one really wants to count those cells anymore. If it's robust, people trust it and use it. And we do it automated, standardized, and in real time. So one sneaky radiologist tried to test us, and he graded like 73 of those pictures by hand, generating one number per image, and it took him 8 hours, and we basically took a minute. So, and then he kind of was convinced and bought it. That's pretty neat. What we generate is actually a fully automated report with lots of numbers, which you can compare different patients, generate better like support. But the question here is like how to actually make a medical grade TensorFlow model, and what does medical grade actually mean? The problem is, in this case, also death by overfitting, I called it, because if you do a wrong prediction on Netflix, like you die of boredom. But if we do a wrong prediction, you might like lose a knee. So we gotta be precise here, and it's a little difficult because we have not so many images with low information content, ambiguous labels because doctors often disagree. And you need a lot of domain expertise to actually generate those labels, and there's hard to obtain because patients have rights and they don't want to give their data. And with that, we're gonna just transform it into a precise and robust medical benefit, which is quick local inference on the CPU, and you can actually prove that you won't kill anyone. And we do that by using magic in order to get like to a, well, medical product, right? But let's look in detail how that actually works. So first of all, if you look at normal images, they are rich in features. They have like intricate details. They are actually RGB, and they are two-dimensional representations of a three-dimensional object. You can use a bunch of pre-trained models, which Google spent lots of money on training it. And there are huge annotated databases of birds and whatever. And also you can generate those labels rather easily if you just want to locate the bird on this image. It's rather easy. Not so much for X-rays. So they are pretty featureless, low contrasty things, which are grayscale, so you have like 2 channels less of information. And at the same time, the beauty of X-ray is that you actually transpose a 3-dimensional object on a 2-dimensional sphere. So you have actually a lot less information to begin with to predict something pretty convoluted. You can not really use those models from real-world objects just because they are, well, even the first layers are pretty trained to much different details. And also, well, we have restricted access to only little label images and labels. And the labels, that's what we did because we come from science. We gave like a bunch of doctors the same images, and they had to come up with the same, they should be able to come up with the same grade on the same image. However, the agreement rate among physicians was only 30%. So yeah, that makes you question a little bit about like the labels which are out there, and that's our daily challenge. So how do we actually succeed in making that robust? And robustness is our main goal. Basically by divide and conquer. What you already pointed out, we can add localized information. It's not the first time we look at a knee. We know how a knee looks, and if we can pinpoint the algorithm to this specific point, we can save a lot of training data. Then we basically segment the knee. So we already talked about semantic segmentation. It just assigns a class to every pixel in the image. And then we actually patented a lot of ROIs, which we place on the image in order to then go full paranoid and make, for each sub-problem, custom networks, feature engineering, and custom losses. So we kind of add redundancy by adding different, have a vote of different models on the same problem. We do ensembles in order to basically simulate different doctors grading the same image. And then we use custom losses which minimize the disagreement between 3 classifiers, or in this case the dice score, and that's the name which you came, or the algorithm you came up with yourself. It's kind of just a metric which allows you to, let's say you have a picture where there's 100 pixels and 1 pixel is only the class that you want to predict, then by accuracy you're always 99% correct if you predict only black, and that's really shitty to optimize, so it's a different score and it works really well. And we got the tip from Amsterdam as well, so giving it back. Thanks. Yeah, so common architectures, we're doing a little transfer learning here because that's what we already saw. It's the UNet, which is published by Ronneberg et al. Already 1,500 citations of this guy because it works really, really well. It's an autoencoder, and what happens is that you always transpose like the pixel-wise detail to the output of the model, and as such it can assign like the small level details to the classification which is generated down here. Let's look at how it basically looks like if you look at the activations of each map. So here you see basic representations which get more and more abstract, and if you look down here, it already figured out how cartilage, for example, where it is in the picture, and then in the end you end up with a classification. What we also do is anomaly detection, where you use like a huge bias in your data in order to turn it to an advantage. So in this case, if you have this example from our kitchen, you train it on only unhealthy things and it is very good at detecting healthy things. And we do the opposite. We take like only healthy knees in order to detect unhealthy things on knees. And yes, we're sponsored by Red Bull. Anyhow. Great. So you do all that, and then you have a great product which you can start to sell, which is sadly not true because that's only part of the equation. So how to actually make a product out of that? First of all, you got to know what problems to solve. So you got to have a lot of medical disease, not medical disease, medical expertise to know who to ask, what problems are actually worth solving, and how to solve them. Then you go into the fun part where you actually solve the problem. And then you have to convince the people that you solved the problem by doing publications. You have to do scientific networking. And once you did that, you have to convince the people to actually buy your product. And for that, you have to put in a lot of IT expertise in order to bring it to their workflow, which is usually doctors don't like the cloud, so you have to do the inference on their CPU and all kinds of crazy stuff until it's working how they want it. Before they can pay, you have to certify the whole thing, and then you can think about earning money. So we already went through that whole thing once, and we want to repeat it more difficult this time. Yeah, so that's what we do. Yeah, so how to earn money? The certification is pretty arduous, I have to say. Its success probability is measured in kilos of printed paperwork. And just some of the fun activities we have to do is to document and look at the harm of each of the 1,300 bugs of TensorFlow, what it would pose to the patient. So we go through the bug list and come up with reasons why it might harm someone in the future, and then we have to document the harm of bugs which are not yet reported but still might be there, and then we have to document on how to document those, and then we have to document on the process of how to document the documentation, and then we have a person who monitors the process on how to document that, and so forth. So it's really like wasting a lot of energy and effort in order to actually like figure out really everything beforehand until you really hurt someone. And then you repeat it for everything else you use, like NumPy, Python, C++, Java, whatever. And the motivation is kind of that the healthcare expenditure is trillion dollars. So we might find our rent there in the future. The last mile delivery to the doctor is then rather easy again, because there's something called the Amazon for AI, which is really nice for deploying those things. What we do is like we put our inference models into Docker images, and they have a backend where you can basically deploy them on AWS, and you have a developer portal, and they reach out to 2,000 major US hospitals where they actually do all the bothering stuff of putting a local inference server with GPUs and take care of all the security and stuff. You just really don't want to do that. Yeah, so, also we got featured in the NVIDIA GTC conference, so we're obviously in the same league as NASA and Airbus here, so we are actually this healer here. You can watch it on ImageBiopsyLab.com. And that's like the team which made it possible. We are pretty diverse set of skills, and that's like where the magic is happening. That's 6 times in a row Employee of the Month, Ulf, which has our GPU. No one yet could tackle his level of enthusiasm. Nonetheless, if you want to help your fellow humans actually with AI, then surprise, we are hiring, and please contact us if you're up for this challenge and well, doing something great together. Thank you very much.
Thanks, Christoph. This was just great. Like, looks really good. Looks really moving fast forward, and we hope to see really a lot of success here.
By back propagation.
Sorry?
No.
Let's see what questions our audience comes up with.
I can just ask, where can I find your publications? Richard here is responsible for that, so we can well, he's going to present on the ORC, and can you say something about it?
Yeah, so we haven't really published too much yet, because in the medical field you have to pretty much tell everyone what you did. So it was just limited to abstracts, which we published the last couple of years, and oral presentations. An archive, I think there's one publication archive, but it was just a first paper.
I would have a question regarding your patent. You said that you had a patent. Was it software only, or did you have some hardware developments as well?
Hardware? No. Actually, well, no. Yeah. So, good question. So, if like the good old GIGO, like garbage in, garbage out, also applies to us, and we noticed that if you take an image like this or this, matters actually for our analysis. So we gathered with a hardware producing company who also does medical devices, and actually developed a knee positioner which standardizes the way of acquiring the image in order to have a standardized way of assessing the image. So we're going really great length here in order to do proper science, I think. And regarding the patent, it's a software patent where we really just the placement of the ROIs. It's, patents are a thing, but it's, let's see if it helps. It's just, we claimed it, and because it works in this way.
Yep, another question here.
Hello, you mentioned your scarce data sources. So where do you get your data to train your models? Sufficient data?
So there are 3 different ways for medical data acquisition. The first one is big Kaggle competitions, where actually big study consortia get together, label their data, and put it out there for people to train on. Also, that's the reason why there's a lot of chest X-ray companies out there. But still, there are already a lot of papers on why the labels on this chest X-ray data set is actually also wrong, and that the doctors themselves labeled it wrongly there as well. So what we rely on is multi-center osteoarthritis studies, which have the same patient for 5 years coming back and taking a lot of X-rays, MRT, and so forth. And the third thing which we are pushing a lot is to actually go and engage in scientific collaborations. So we provide a labeling tool to people who label all the differential diagnosis, because there's much more going on. And when we sell our product, even the radiologists who just paid us are labeling us data, because they they love technology, radiologists at least, and they want to be part of this whole thing. So that's what we try to do.
Is there any competition in the knee X-ray field, and are there still body parts free for other startups to purchase?
Actually, it's a pretty Wild West experience for me, because every problem is really hard to solve because of those data limitations and the image problems and the labeling problems. So there are so many body parts and so many different diagnoses that it's very sparsely settled yet. And we just have, like, we spun off from another company who has built X-ray machines. So for us, it was logical to use our expertise in bone diseases to do that. And so far, there's a lot of space still left, and we want to claim what's possible as quick as possible.
More questions popping up.
You said that you had the loss for the ensembles to have as little like disagreement as possible. So how did you merge that into the whole overall loss sort of thing? Because on the one side you want the model to correct the right thing, and on the other side you want to have as little disagreement as possible. And you don't want the bias that they all vote on the same wrong thing.
True, yeah. It's called, you basically transfer your categories which you had into a kappa factor. It's basically just a mathematical measurement of exactly this disagreement, and also like if you're if the real value is 3 and you vote for a 0, that's penalized more than if you vote for a 2, for example. So that's kind of how you get around and in getting more closer to the real value as possible.
I was wondering if you also made any surprise discoveries, like the people with the retina photos recently, where they found out, where doctors were surprised that you could predict the age and the gender of the person's retina photo. I think it was published in Nature just a few weeks ago.
Yeah, the Nature Communications, yes. So what they do is they give the big overall score, like a score from 0 to 4, which is like the KL grade, and it's composed of 4 sub-scores, which is like how the bone changes, if there are things growing at the side, how narrow is the cleft, and how deformed is the stuff, and we do all those 4 sub things individually, and then go back and predict the overall score. So we go bottom up, because we come from feature engineering, and we tried it for a long time, and it kind of worked, but neural networks are just so much more robust. So they came top down, just predicting the score, and that works great. But what we saw is that doctors are not researchers in that regard. They want to have things they already know, and if you come with a black box which puts shiny attention maps and whatever on there, they are a little bit scared and skeptical, and as such we rather rely on millimeter measurements, which they already did back then. Like they put a ruler on the thing and measured it manually. So we stick to standards from the 60s basically, in order to comply with the standards of the medical procedure. What they did is kind of a nice research, but we stick to the medical practice in this field.
Okay, there was another question here, right?
Yeah, this might be a follow-up to the question we just had. So you showed us the segmentation images. Is that the actual result that you're selling to doctors? Because you said you have a product already in the market, or do you generate measurements from those segmentation data that you then sell, or what's the actual product?
The second one. We use the doctor doesn't see anything from the deep learning except that it's working very robustly and pretty precisely. With feature engineering, it was often not detecting the knee, or the landmarks were not properly set, and now we really got to over 95% of accuracy at detecting the knee, at setting the reference frame, and what we're actually selling is really just those 4 individual measurements, which then compose to the disease grade, plus additional traditional measurements like millimeters and these kind of things. So pretty traditional stuff, which they already know because they want to fit it into their normal workflow. They don't want to learn new things or have, or at least from our expectations right now. So yeah, we stick to traditional matrices, but we use deep learning to make it robust and create those in the first place.
And this is the product that you're already selling here, and you're trying to get FDA approval for that?
Exactly, yeah. So right now we use it as a clinical decision support system. So people, if they have the possibility to click then correct, you're not actually replacing the doctor, but you're just giving a suggestion. And as such, you can wiggle yourself out and say we are class 1, which is much easier to certify. But now what we want to do in order to, because they don't want to have an additional software, etc., which they have to switch to another screen. So we want to make a black box where the picture comes in and the report comes out. That's going to be much, much easier to bring to a doctor's office, but it has to be also very, very precise and robust in order to to be sold properly. And that's what we're working on, and for that we got to validate everything.
Yeah, and the licensing for that is a different beast, so that's the hard part, yeah.
Exactly, yeah.
Do we have other questions? One here, one last one.
Hi. So you showed that the doctors have accuracy 30% in classifying, or I don't know what was the 30% for, if it's like predicting correctly that the disease will come in the future?
No, that was just having a picture and having 3 doctors say a number between 0 and 4, and the agreement between those was 30%. So in only 3 of the cases, 3 doctors said the same number of disease state to the same picture. So that's kind of the inter and intra-rater variability which we measured with this.
And do you have some kind of evaluation of your system, that how good it is when you have this kind of ground truth?
So the thing is that we try to do bottom up and really solve every problem at the same time, which never happens in the medical practice. They just look at the picture and just give a score for the overall thing. So what we saw is if we break it down to individual problems, like only narrowing the focus down to a certain part of the knee and presenting them with this problem, they say different things than if you show them the complete knee, because they are biased by, like if the joint space width is narrow, then well, probably also the other things are there. So they have very strong correlations between one score and the other, which are not backed up by the real image data, because doctors are just biased. They have to work quickly, and yeah, so that's what we're dealing with.
Thanks. And can I have one quick question? So the niche is solved, and you say you have new challenges. So is there some other part you want to focus on, or
so
something in the future?
The first obvious thing would be osteoarthritis can happen everywhere in the body, and in this case we can actually do transfer learning because we trained our models on hand segmented data of X-rays. So going to another X-ray would be pretty simple. The next thing is going to animals. There's a lot of studies. Just last week there was also that obesity is actually causing osteoarthritis due to like a constant state of inflammation in the body, and they do those studies on mice. So getting a correct assessment of knee osteoarthritis in mice would be actually also a problem we can solve and provide. Like what researchers are looking for is like standardized, robust, reproducible data, and that's what we can provide with this. And as such, they can lower the noise in their system during research. They can decrease the sample size and come quicker to a more accurate solution. And yeah, that's why we're selling it to researchers and doctors alike.
Thank you very much, Christoph. An applause for our speaker again. Our speakers will be around. There's also Richard here from ImageBiopsyLab. So if you're interested in a position they're offering, you can talk to them after this section that is coming up right now. Also, Anouk is here for a while. She has to leave a little bit earlier, but if you have a question, if you have questions to our speakers, there should be time after we finish with the final part of this evening. And the final part of this evening is latest news and hot topics. So my nice co-hosts Alex and Jan here prepared a couple of things that were coming up in the past, in this case, 1.5 months since we did our last meetup. And yeah, as you will see, it's always quite a high number of things that are just popping up from 1 month to the next. So deep learning, as you probably know, is a really, really fast developing field. And yeah, we're gonna see what Alex and Jan are presenting today, what came up recently. Okay.
Yeah, the first hot topic, it's from a personal connection. When I read my Twitter feed, I stumbled across this, and it's definitely not the hottest topic today. We have had very, very great talks today, but this one is like, I've been playing guitar, and one of the things you do when you're at home in a flat in Vienna, you can't play with an 120 watt amplifier. You have to use headphones. And then when you grow older and you have limited space, you don't want to have all these gears, so you reduce it to a laptop and you have your VST plugins and you emulate an amplifier. You want to have that sound, but you want to have all these gears standing around. So amplifying an amplifier is you just emulate the sound created by a certain amplifier. And the paper is not the greatest one, and the approach is not the greatest one, but the author took really care in explaining the problem. So I understood then that it's a real problem to create those physical-based models to emulate an amplifier. And what he did is he used neural networks, he used an LSTM to learn the function to emulate an amplifier. And this turned out to be really a really easy task. So he had an error, a mean squared error of 1%, and this is the emulated signal. So the orange one is the target, the ground truth value from the signal, and the blue one is the predicted. So great. Then I read, the task was to train this amplifier at full gain. So I think, okay, a noisy amplifier, it's pretty easy to emulate. But then he's also used the same approach to train further parameters using gain and equalizer inputs. So that's a pretty nice approach to emulate and to produce different sounds. And you can use this for different models, for different amplifiers, for different guitar effects. Yeah, it was a nice paper. But the really, really impressive one was this one. And I'm sad that I don't have an hour to talk about this because this was so impressive. It's a paper about a project, deep writing. And this combines so many things in one. Usually there are different tasks like handwritten character recognition. This has been a huge task in the past. And then we have already heard in the deep learning meetups about style transfer, where a model is trained on a given style, like paintings from Van Gogh, and this style is transferred on a photograph, and this photograph is then generated in the same style as the painting of Van Gogh, and spell checking and so on. And this project all integrated those things into one approach. And the aim was to have, where is this? The aim was to have this character recognition of handwritten text, and to add style transfer, or to generate text in. So you can type in on your keyboard, you can type in text, and you have it in your own handwritten style, written on, printed out. And the approach they've taken is, it's really complicated. So after reading it 3 times, I barely understand what they've been doing in these 3 years, and it's on my reading list for the long weekend. They're using a conditional variational recurrent neural network, which is, they have like an LSTM, and they introduce a set of conditional and latent variables, which combines, so they have one model which combines, which decouples the style from the content. So the same model recognizes or learns the content, so the textual input and the style information. And they put it in different latent semantic spaces. And these different latent spaces they can use for text analysis, for character recognition and text analysis, and for style reconstruction. And what they can do is, like, the first one, I'm afraid to press a button. Is it? Yeah, it's this one. Okay. So you can. This is the input sample. This is your handwriting. You can enter in the system, and then this style is learned and transferred to another one. So this is a training example, and a different example from another person. And your style is transferred on this recognized text. The model recognizes this written text and applies the style of your handwriting to this. So this is style transfer. Also here another example. This is the same with digital inputs. So you type in here the text, and your style of handwriting is applied to this digital input text. And the most funny thing is here. So it does spell correction on your handwriting. So you can have spelling correction in handwritten text, and it corrects the text in your own style. So it's really great. So yeah, I meant to keep it short, and I hand over to Jan.
Yeah, cool. So as usual, there are much too many papers to cover, and so this time I focused on one theme, and I'm going to introduce it with a little experiment. So I'm going to show you a couple of images, and try to quickly see if you see a dog there. If you see a dog, then raise your hand, and if it's a cat, then don't raise your hand. So let's start. Do you see a dog? 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 You're all wrong. All the others were correct. So, but for this one, yeah, so the topic is adversarial examples. And in this paper, they showed that when you manipulate an image, so that multiple different image classifiers, in this case they took 10 image classifiers, all think that this is not a cat anymore but a dog, and you show this manipulated image to humans, then they will also get fooled most of the time, at least when you only give them very short amount of time to make their decision. And that's fun. But adversarial examples are not always fun. So this is a more serious example, and this is also connected to the previous talk. And that's a paper called Adversarial Attacks Against Medical Deep Learning Systems. So the usual adversarial examples are not manipulated in a way that humans get fooled by them, but you try to make some minimal changes to an image such that a classifier will classify it differently than a human would. And you try to make these changes as minimal as possible so humans won't even be able to see them, but it causes the image to cross some of the classification boundaries of the classifier. And this paper considers what happens if you do this with medical images. they so in medical images, you will often have some image of skin or of an X-ray, and you want to determine if there's a disease in there or how strong the disease is. And these models are also susceptible to adversarials. So why would you want to do adversarial attacks on medical deep learning systems? You said it was 4.3 trillion US dollars, and they gave a figure of 3.3 trillion US dollars. So there's a lot of money spent on healthcare, and for many of the payments depend on the diagnosis or of the treatment. So people are interested in getting patients with a strong disease or with diseases at all, so they get more money. And in the future, such diagnoses will probably be confirmed by algorithms in order to reduce the possibilities for fraud. So people cannot just claim they see some disease that will be checked by an algorithm. But this also introduces new possibilities for fraud. Because now you can try to manipulate the images so that the algorithms will detect a disease or a stronger diseases than there actually are in the images. And why is it easy to do that? Well, as we also saw in the previous talk, experts often disagree themselves on how strong a disease is. So it's very easy to do some systematic fraud, because people will not really notice. If they manipulate the image so the score gets just a little higher, then the experts will say, yeah, maybe it's that high, okay. And if you do that systematically, you can maybe get more money out of the healthcare system. And another point why it's easy is that medical imaging is highly standardized. So you get, if the knee X-rays will all look pretty similar, so it's pretty easy to mount some attack on that. It's much easier than trying to get adversarial traffic signs, for example, that work for all cars and are all conditions or so. And another reason they gave in the paper is that hospital software infrastructure is very slow to update. So if you manage to mount some attack there, it may take years until they manage to roll out a new software system that doesn't have these defects anymore. And what do they suggest to do about it? Well, there's a lot of research going on trying to come up with algorithms that are less susceptible to adversarial attacks, but there's no universal solution yet. So what they suggest is to try to come up with infrastructural defenses. Have a medical imaging system, like produce a cryptographic sign or a signature of the image, so that you cannot manipulate it afterwards without being detected. Okay, and another interesting attack, that's another paper called Poison Frogs, targeted clean label poisoning attacks on neural networks. So again, an adversarial example is just is an image where you add some minimal amount of changes so that it crosses some classification boundary of a classifier without people noticing it. Now, they saw that you can actually also add such examples to the training set, and then it may cause the classifier that's trained on the image to put the classification boundary somewhere different, so that you can force it to misclassify some specific target image that you wanted to misclassify. And that's an attack you can mount when you can create training examples that will be used by the system, but while the labels are still given by human experts. So, like, I don't know, for some systems it may be enough to just upload some images somewhere on the internet that Google will find them, and then maybe it will end up in the training set of the system you want to attack. And they showed that for networks trained with transfer laning, where you start with a network pre-trained on ImageNet and you only tune the very last layer,
it's even possible to just add a single like poison frog image to the training set, and it will classify your target differently. So here they use the dog as a target, and when you add these manipulated dogs that just look like the original dog, but they are not, you can force the network to classify this one, this one, this one, or this one as a dog, which with very high confidence. For end-to-end learning, where you train all the layers and not just the final one, it gets more difficult. So they had to use multiple poison examples, and also they were much less elegantly created, so they added the poison target image as a watermark by blending it over it. So there's 30% bird in here everywhere. You don't really see it. So humans will still label all of these examples as dogs, and then it will, the system will label the bird as a dog. And now for some more fun example again. I don't know if you remember the cycle GAN. We discussed that in the 11th meetup. I looked it up. And this is a paper called Cycle GAN, a master of steganography. So the idea in Cycle GAN was you train a network on 2 collections of images, or actually multiple networks, so that it can transfer from one domain into the others. For example, from horses to zebras, and from zebras to horses, or from apples to oranges and oranges to apples. And you don't need paired training examples for that. You just need a collection of zebra images, collection of horse images. And it works the following way. There's always a dangling bullet point here. Cool. So you have 2 generators. So it's in the setting of generative adversarial networks. So this is a network that is trained to produce a zebra from a horse, and there is another one that is trained to produce a horse from a zebra. And you have a discriminator that is trained to check whether this is an actual zebra image or it's one that has been generated. So this is trained to not be fooled by the generator, while the generator is trained to fool the discriminator. In that way, it will learn to detect zebras that the discriminator cannot distinguish from actual zebras. And the same way here, you have a discriminator that tries to figure out whether this is an actual horse or one that has been created from a zebra. And then there's a cycle loss. You need that because you want the zebra to look like the horse, just with stripes, and you want the horse to look like the zebra, just without stripes. So you add a cycle loss that checks whether this image looks the same as this image after going through the 2 transformations. So this looks all plausible here, but if we change this, so actually, yeah, if we look for the other direction, there's also cycle loss. So now the network is trained to produce exactly the same zebra here as it got here. How is it going to do that? How should it preserve where the stripes are if there are no stripes in here? And the authors of this paper said there must be something the network is doing to solve this. And they found out, so they used a different task here where it was also in the Cycle GAN paper, where they convert satellite images into maps and back into satellite images. And they found out the network is actually adding some information here. You can use it, you can visualize it if you do some contrast enhancement. So it looks like a normal map here, but actually there's a lot of information about what the buildings look like hidden in the image in a way that the discriminator cannot see it, and in the way that we don't see it. So neural networks also manage to use adversarial examples to their advantage if you don't pay attention. Now just 2 very brief technical slides. Most of you who are in deep learning will probably know QDNN. It's a library provided by NVIDIA. They don't only build the GPUs that people are supposed to do deep learning on according to the NVIDIA, they also provide a library with a lot of deep learning primitives like convolutions that are very fast, and it's closed source. So AMD, for example, cannot copy their ideas, and also provide a very fast deep learning library for their hardware. One interesting thing about it is they have implemented different algorithms, and for convolution, for example, and depending on the amount of free GPU memory, they will use a faster algorithm that uses more memory, or a slower algorithm that uses less memory. And those guys figured out that if you put a wrapper library around it that splits up your mini batches into smaller mini batches and feed them into the QDNN library sequentially, it will choose a faster algorithm and in total be faster than if you just use QDNN on their own. That's a nice hack. I always like these hacks, but it's just necessary because QDNN is closed source. Otherwise, you could just manipulate QDNN yourself, of course. And this brings us to the next slide. This was introduced recently and added to PyTorch. It's called tensor comprehensions. It comes, if you know Python, you know list comprehensions. So they call it tensor comprehensions, which is like a multi-dimensional list comprehension where you specify what the output of some tensor operation should look like in some kind of Einstein notation. And what they do then is they generate CUDA kernels from the specification, different ones, and they do some genetic algorithm optimization to actually produce a CUDA kernel that computes this function in the minimum amount of time. And it's often faster than QDNN, and this now allows people to try things that are not in QDNN, for example, and do useful experiments with them instead of when you roll out your own implementation, it's often too slow. Yeah, so this kind of sidesteps the limitations of using closed source implementations. And as always, there's a lot of more. You can check Archive Sanity or deeplearn.org, or you can go to Reddit, our machine learning. There are a lot of papers discussed. Cool. Thank you.
Thank you very much, Jan and Alex. Yeah, this brings us to the end of the meetup, almost, because there's more drinks and we want you to network and exchange ideas. Before that, I want to thank our really great speakers this evening. We're like, every time we get better speakers. Thanks Anouk Visser from Birds.ai to come here from Delft/Amsterdam in the Netherlands just for tonight. Thanks Christoph Götz and Richard also from ImageBiopsyLab. Thanks the team of Wien Energie, Michael Elias, Wolfgang Zerha, our Alexander Kirchner is somewhere here too, or did he leave? Yeah, and everyone else who supported this evening tonight. And yeah, at the end I want to point you once again to the next meetup, which is in exactly 2 weeks. And we have the great opportunity to finally discuss what's going on, ethics and bias in AI, and what to be warned of and what to consider when you start creating your own neural networks and your own deep learning based programs and want to bring them to the market like these wonderful companies that we heard today. So you need to take care about a lot of things, and we want to point this out in this panel discussion on May 17th at 6:30 as usual. Thanks for being here. Spread the word and yeah, stay with us to exchange ideas. See you next time.